Akihito Soeda. I'm from NII, which is in Tokyo. I'm also a faculty at Sokendai. So I'd like to thank all the organizers for giving this wonderful opportunity to talk about my work, I should say. And yeah, so by the way, so first of all, and also like I congratulate all of you for making this far, like Friday afternoon in Okinawa. You guys are like 3 meters away from the ocean, but you still decided to here. So I like your dedication, right? By the way, this is a picture I took from a hotel room, so it's also someone from this who was attending this someone described Okinawa as a paradise, and I kind of agree. It's a nice place. So I have 3 slides on keynote presentation. The rest will be just handwritten, because my talk is going to be about theoretical work, and I'm sure you don't want like millions of slides and with all the theorem, proof. So I'll try to be more relaxed and casual, and I've decided to use handwritten lectures for that purpose. All right, so let me go on. Okay, so let me just give you a bit of background of how I came to this topic, right? So I always like to, since I was a kid, I always like to know how things work and how things function. And the physics for me was like a natural topic to choose to so that supposedly physics explains everything about the universe. Okay, so why not learn it? And then went to the physics department, and obviously quantum mechanics is the supposedly the most advanced topic in physics. And then I learned about quantum information. Okay, but because one of the reasons I like doing quantum mechanics was because it's so different from what I knew about the reality, I would say in a classical sense. So so I wanted to do that. And entanglement, as you already know, is like a very characteristic property of quantum mechanics that sets apart from classical theory. Okay, so I want to research on quantum entanglement, and so I went to grad school, which I joined a group that works on entanglement theory, and this was back in 2006. Okay, now right, so they were doing entanglement theory, but I soon realized that maybe entanglement cannot capture everything that it's characteristic about the quantum theory, especially if you want to study, if you want to learn where the quantum advantage comes in terms of information processing. Well, a state is important, of course, and entanglement searching is some form of resource, but it wasn't, it was obvious to me that that's not the, that won't be the entire story. And then, I went to look at I decided to look at the quantum operations, because what actually drives the computation is quantum operations. Okay, so I thought, well, if I understand quantum operations, I will understand something more about quantum computation and information processing in general. Okay, so I was in this quantum entanglement group, wanted to do quantum operations, so I thought I'll just merge 2 things somehow, and then decided to study quantum operation that happens in this distributed setting. Okay, now, so that's what I'm going to be talking about. So what is it about the, so what makes, what are some key properties of quantum operation that you can do in distributed setting? All right, now, okay, the first topic that I would say is most related to this topic that I've encountered is making controlled unitaries. Okay, everyone knows what controlled unitaries, right? So, in some sense, it looks like this, or in the matrix forms, you have some, unitary that is encoded in this part. So basically, if it has you have some target, so control and target qubit and target system, and it looks like this. Right, so when the control qubit is in 0 state, it does nothing. When it's 1, it does unitary. Okay, everybody knows this. But this came when my group was talking about the obfuscation of unitary. So I think Mina's sort of mentioned obfuscation once. At least I remember. I don't know if she's discussed about this, but obfuscation is the idea of making something look like completely unknown as much as possible. So in that particular case, my group was kind of discussing, how to make a circuit obfuscated. So they were studying, so here's a description of a quantum circuit, and the idea is to make it look completely, unintelligent to people who are like not designed, to those people who have not actually designed the system. Okay, so it was like kind of like sharing a software to other people. So even a quantum program would design a program, and it would break it down to a quantum circuit and want to share it. She wants to share that to the customers, but at the same time, maybe the software program wants to protect that this exact circuit, or at least not the circuits, but the actual software. Not reveal what it actually does. Okay, so this was just kind of a initial question. Okay, but actually, deciding, knowing, identifying what actually this circuit does is usually a difficult problem. It's QMA complete in some formulation. So it's a really difficult question. Okay, but maybe you don't need to know everything about your unitary. Maybe you only need to learn about some specific property of unitary. Okay. Yeah. So one way to extract some property about unitary is to do quantum phase estimation. So this U contains some information that's hidden that the software programmer decided to hide. And then you as an attacker would try to implement the quantum phase estimation. All right, so but you know how to implement U, but can you make this control unitary? So the first try, I thought, okay, to be honest, I thought this was a very simple idea. So let's see what we can do first. Okay, so then I thought that we add Ancilla. So I will use this controlled swap operation or Frederick gate, if you like. And then I'll use this unitary here, right? So the idea is that when the control qubit is in the 0 state, this swap operation is basically deactivated, and the target state will basically travel all the way across. But if the control qubit is in the 1 state, this swap operation is activated, hence this target state will travel all the way down to this unitary, and it would go through. And of course, once we're done, that we need to bring this up. So we add one more control swap operation, like this. All right, so this looks like a viable solution, but can you see if there's a problem? Can you do this calculation immediately and see where the problem is? Well, it's a Friday afternoon, so maybe you don't want to use the brain to do it. So I'll do that calculation for you. All right, let's do this. So, all right, so let's divide this into several steps and do the calculation. All right. So let's see how we can do this. So the first step is to have the calculation here somewhere. So just make sure I don't get it wrong. All right, cool. So let's see. So the initial state is, let's say you have a alpha 0 plus beta 1. That's for the control system. And the target is in some arbitrary state, psi. And the ancilla is in 0 state. That's the initial state. Okay. Now you apply this control swap operation. Okay. So let's, okay. For that, I should say let's expand this. All right. So now let's apply this control swap operation. So the first term, because the control is in the 0 state, the swap is deactivated, so this doesn't change. All right. The second term, now the control qubit is in the 1 state, so the swap should change the state of these two subsystems, and you get this. Oh yes, and I have implicitly assumed that the ancilla and the target system have the same dimension. All right. Now let's apply U, right? So U applies on the ancilla state. So that part is simple. U on psi. All right. All right. So finally, the last remaining step is to apply a control swap operation, and I will not repeat the exact action of control unitary, a control swap operation, but I'll just write the answer. Okay. All right. Now, ideally, we want this to equal this. And times, some state. All right. So this is what we want this to be, ideally. So we have basically the initial state has been, transformed this particular state. So you can see that U is applied to target state only when the control cube is 1. And I want the ancilla state to be basically disentangled, separable. But no matter how you choose this eta, right, it cannot equal to both this state and this state simultaneously. So you can see that, this is, I would say, arguably a naive implementation, a naive trial for implementing control unit operation just doesn't work, okay? Now, of course, this is not a proper, go ahead.
So maybe simplicity, but what's the metric of success? So when would success be achieved?
So the metric of success is basically we want this to equal something like this. So we want effect to be something like this, some eta. So that's the metric of success, right? That's what we want. Go ahead, please. I know what I did because I stepped on the HDMI cable. So I was told that this Seaside house is going under renovation quite soon, and hopefully this kind of issue will be rectified, so we don't have to worry about some speakers stepping on the cable. All right. Anyway, so yeah, so that's the metric that we want. So that's the task. We want this circuit to be something like this. But as we saw in the calculation that follows, that it is basically this can't happen. I mean, okay. But maybe we didn't try hard enough, maybe control swap operation, if it worked, fine, but there are so many other different circuits to try for. So would it be possible? Well, actually, retrospectively, this should have been kind of a simple question, but simple to answer because what we're trying to do, right? So we're trying to basically make unitary into control unitary, right? And there's actually a simple no-go proof without ever going to some complicated discussion is that if this were actually possible, then you're making you're making this. So if this happens, right, the change in the phase of unitary appears as a relative phase in control unitary, but the unitary the phase of this unitary as input should be a global phase. So there should be no physical process that distinguish the global phase of a unitary, right? So if this transformation was possible, then that means you can convert a global phase to a relative phase. Hence, it just doesn't work. Okay, so that's kind of a simple no-go proof for this. But if it, but then again, then we ask, well, maybe we were too naive. Okay, maybe we were too naive. Maybe we could have just changed the definition of unitary control unitary a little bit and make things work. So for example, so instead of taking unit So instead of taking unitary to to the standard form of control unitary, maybe I don't know. We allow some extra phase to sort of like cancel the global phase, right? Maybe this is possible. So now, would this be possible? I don't know. Okay, actually, so it turns out that this is not possible, at least if you require exact deterministic, and if you only use a single call. So single call, I mean that a single use of this input unitary, okay? So this is, if you require these assumptions, then this is not possible. I won't give you the full proof, but I'll do enough so that you get a sense of where this impossibility comes from. Okay, so what we want to do is basically, without loss of generality, this is control, target, and Scylla, and then you have these D1, and apply unitary here. So in general, whatever you do, if you require this exact deterministic single use call, then any circuit attempt would look like this. Okay, and we want this to be in a control unitary. Right, so, well, up to some phase that corrects for the global phase of unitary. All right, cool. So, okay, let's see. Now let's, how do we do this? Okay, so it's, so as a matrix multiplication, it should look like this. It's whenever you do this, you write circuit, which goes from left to right. When you write equation, it's actually from right to left. So you have to sort of switch the orders. But if you know this as a multiplication of matrices, it should look like this. Okay. Now, suppose that your unitary is a single cube unitary. So in that case, you should be able to write expand your unitary using Pauli matrices like this. Okay. Yes, please. Okay. Okay, that's right. So if I were to be more more proper, I would need to add these two. But thanks for asking. Yes. Oh, well, actually, someone that's paying attention. That's good to know. Anyway, so this is just standard mathematics. So you can always decompose unitaries into using Pauli matrices. All right, good. Now let's use the distributive property. Right, this is just multiplication matrices, so we should be able to use distributive properties. Or so what do we get? So we get this, right? Okay, let's V2. So again, but I will skip the tensor so for the reasons of brevity. Right. Now, this is just simple distributive property, but now what you should notice is that this is actually, V1 times some unitary times V2. So it should follow the, if V1 and V2 were to do this in a quantization properly, then this should equal to, what we want, right? So this would equal A times like this, and then I need to add this some phase, right? What's it? Okay, good. All right, so this is what should be equal. Now, okay, let's just multiply everything and add everything. And what do we get? And what we get is that is this. All right, cool. Now you can see that, this might be a unitary if all these were like, for example, it's one, right? If maybe, maybe this phi function was defined so that it returns one on these specific cases. So this would be unitary, but no matter what you do, this cannot be, equal to one, right? So you can see that, we thought we relaxed the requirement by allowing this arbitrary phase, but even this case, if you require that we want this transparent to be exact, deterministic, and a single code, it doesn't work. All right, cool. Okay, so okay, well, we didn't want to give up. So what else can we do? Okay, I'm not going to all of them, but for example, so we require these things. Maybe we can make something to be approximate, right? But so actually, if you allow something to be approximate, then is always kind of a cheat solution. That is to allow some big error. If you allow big error, then any operation is almost a solution. So that's like kind of a cheating, right? To solve. But so what we want to control the degree of this error. Okay. So so something a bit smarter to do is to use a tomography. So what you do is you take a unitary, but instead of applying that, including in this circuit directly, you do kind of you use it offline to learn about what this unitary might be. Of course, with a single call, you cannot learn everything about unitary, but that's better than nothing. And with that knowledge, you construct, the necessary circuit sequence that you need to implement, then apply that on your input. So that's kind of an approximate solution, but it's deterministic. All right. And something else to do is to get rid of this deterministic solution. Now, this is more difficult to solve, but several years ago, in fact, a group from Israel, I believe, actually were able to prove that if you require the exactness, and then probabilistic and multiple calls of unitary cannot give you this this control unitary from unknown unitary. Okay, this is more much more involved than what I just shown you here, but there is some element of this proof in it. In that sense that the geometry of this is very different from what is required by this ideal control unitary. Okay, that's a very hand-wavy argument, but that's kind of the gist of the proof. Right, and what else? Oh yeah. So one thing that we can relax here is that maybe, so first of all, so far up to now, we assume that this unitary is arbitrary in the sense arbitrary up to some dimension. I don't know, but maybe you know something about the unitary beforehand. For example, you can already see in this proof that, not proof, but in this calculation that if you know like one eigenvector of this unitary, then you can set it so that this is equal to maybe this U has one eigenvector that's zero state, right? And then actually, this actually factors out safely, and then you get back, control unitary up to some global phase, up to some relative phase. Right. So like there are some, a few ways to relax your requirements and make it still possible. Right. But okay. So any questions so far? So this was all about. Please go ahead.
Similar to the one we wanted to obtain if monitoring.
Say it again.
If we make the trace on the last qubit.
If you make a trace on the last qubit, yes.
If the density matrix of this state is the same as the one we would obtain if we directly trace.
So in general, it's not. In general, it's not. Yes, and that's pretty much the whole point of this no-go proof. Yeah. Yeah. So the question was, what happens when you trace out this unsealed state and unsealed system, and do you get back the density matrix that you're supposed to? And the answer is no. And that's pretty much the message of the proof. All right. Okay. Now, so the reason I brought this kind of I brought this topic was because I thought it would be appropriate if there is kind of a client-server scenario in doing this calculation. So you have some server in the cloud that implements some unitary, and then some client, right, which has something, and you will make some quantum query to server, and server returns this result back to the client, and then maybe client can utilize whatever the server is providing to the client, and then again maybe server would not necessarily reveal everything to client. I cannot imagine, for example, a quantum Google, for example, revealing everything that they're doing to their customers. So maybe so, but still. This could be this was a kind of the scenario that we had in mind. So okay, so in future maybe we have a distributed cloud system. All right, then this kind of theory might be interesting. But should you care when people are trying to build one computer? Well, yeah. Well, my answer to this is probably yes if you want to go large scale, and let me give you. Discuss why that might be the case. All right, so as quantum programs become large, it will start to look something like this. Doesn't matter what it is, what they actually do, but the point is that as function requirement become more sophisticated, the exact quantum circuit to achieve that will also be more complicated, right? And if maybe today someone implements some function using this circuit, but maybe tomorrow they come up with a better quantum circuit, and that looks completely different. Yes, but maybe if you're the only programmer who's doing this programming for quantum computer, maybe you can keep track of everything that you do. But as team becomes large, and there are multiple people working on the programming, and do you really want to require that you're programming that under the assumption that you know everything about the quantum circuit? I don't know. It's probably might be difficult. So this kind of quantum programming, assuming some unknown unitary, could be useful if you, for example, want to design software libraries for quantum programming. Well, this is just some thought. Okay. So arguably, what I have shown you so far is correct, but it's a bit ad hoc, right? Like, do you want to be bothered with finding a no-go theorem whenever you have difficult problem? Or I would say probably no, right? So you would want something a little bit more systematic. So the best systematic solution to this is actually what arguably is using semi-definite programming. So who here knows about semi-definite programming? Raise your hand. All right, some, but okay. So there are many versions of semi-definite programming which are equivalent at mathematical level. I'll just show you one version that is most relevant to what we're going to talk about, or semi-definite programming. Which is I most likely say it's SDP for short. All right, so semi-definite programming is this, right? So you maximize on this. Right, so that's a basic formulation. So so now the definition of this is that this inner product is defined by this function. So you take the Hermitian conjugate of A and then apply that, multiply that with X, and they take the trace of the whole thing. So that's the inner product. And this function phi is a function that takes a matrix input matrix, but there is an extra assumption that this should be linear and a hermiticity preserving. So that's just another way of saying that if you input a Hermitian matrix to this function phi, then you always get a Hermitian matrix out. Okay, that's the definition. So maybe it's not so clear at this point why this is related to this higher order programming, but I'll get back to this in a moment. But what's nice about this formulation is that if you can formulate in this way, there are many numerical solvers to give you this, to find the solution, and it's polynomial in the number of variables and a number of constants. The constant in this case is basically anything that's required to specify phi A and B. Okay, but so it's polynomial in that sense. Right. Right. So there is actually another nice property about this STP, namely that there is what's called a dual problem, and you can show that this max is bounded by the solution of the dual problem. So numerically, why this is important is that it's in many optimization techniques that's not STP. It's difficult to assess how good your numerical solution is to true optimal. But in the case of STP, numerical solvers usually give you also the solution to the dual problem. So you can compare. You can look at the solution to this, which is called primal problem versus dual problem, and it gives you a solution to each of these problems. You can see how different these two numbers are. If they're close, then that gives you a very strong confidence that your numerical solution is close to the optimal. Okay, so that's some nice property about your STP. All right. I'll come back to this if we have more time, but anyways, so this is STP. So the question now here is how to formulate the question on finding the circuit that you want in terms of this STP. And this becomes a little bit tricky, but well, I hope you enjoy the rest of the discussion. So any questions so far about STP? I mean, just the formulation, right? So, all right, so before we go on about how to do this for finding a general circuit, let's go to the simplest case, right? To back to the basics of CPTP maps. So where is that? Yeah, so CPTP map and Choi operator and SDP. Okay. So this is kind of a good exercise to refresh your memory about how this finding circuit is related to the SDP. All right, so let lambda be a CPTP map. Does anybody know what CPTP stands for? It stands for complete positive trace preserving map. If you don't know, sorry, I don't think I have enough time to go back to it, but it's it's arguably the most most general form of deterministic quantum operation that you can implement. All right, and then the Choi operator for this is defined by Choi state is defined by like this. So this is maximum entangled state between these two subsystems, and you apply this lambda on one of the particles of the maximum entangled state, and this gives you one state, right? And this state basically encodes all the information that is necessary to specify this map lambda. And I'll just call it C12. And 12 refers to the Hilbert spaces of these two subsystems. All right. So if lambda is a CPTP map, then it has this property that if you take the trace of two, the second subsystem, it gives you the identity on the first system, and also because this is a state, and it obviously must be a positive semi-definite, right? Now, what's important for our case that converse is also true. So whenever you have some permission matrix with only the non-negative eigenvalues and has this satisfied this quantity, it actually refers to some. So the map corresponding to this particular operator is actually a CPTP map. So that's kind of important. Now, I don't know if it's obvious to you at this point, but this is in fact as the constraint that's compatible with SDP, right? So again, let's remember, right? So this is the constraint. So we want the variables to be positive semi-definite, which is satisfied for the CPTP map scenario, and we want this equality to be defined by some linear map on this positive semi-definite variables. And also it must be this linear and Hermitian preserving, but this is usually very easy to satisfy unless you explicitly do something like multiply complex the imaginary number I, right? So is it phi? For example, that's so something that's not Hermitian preserving is to multiply your matrix by the input matrix by some complex number. That's not Hermitian preserving, but don't do that. Okay, so. Usually this is not the most difficult part. So if it's linear usually, then it's usually you're okay, you're good to go. So this partial trace function is linear in terms of the input variable. Okay, and this should equal some constant matrix which is satisfied. So this formulation is actually SDP compatible. All right. Okay, let's see. Right now, right. So if you can find such operator that satisfies these constraints, then there exists a quantum circuit using involving only unitary operation that implements this. Okay. So how do we do this? So for that, okay, let's remember how to, so we need to remember how we do purification. So purification is basically, if you, so let's refresh our memory. So if you have a purification, then you have a positive semi-definite matrix, then you want to find some vector. Yeah, let's say that this row is on A, Hilbert space A, such that if you take the partial trace on R, then you get the original value. This is so psi AR is called a purification of rho. Now, this is the word purification is also used in the context of entanglement purification. It can be a little bit confusing, but when I say purification in this talk, it will be always purification of the density matrix, so there's no confusion. Anyway, all right. So let's Then how do we find purification? All right. So what we first do is we do the spectrum decomposition. That is, you take rho and try and find the eigenvalues, which I label as Ri, and the corresponding eigenvectors Ui. And this can be done, I don't know, using, for example, solving the characteristics polynomial to find the eigenvalues, and then solve a linear equation to find the eigenvector. So standard, there are many ways to find eigenvectors and then eigenvalues, but it's doable. That's the point. Now, positive semi-definite implies that all the eigenvalues are non-negative. Hence, what's nice about this is that the root is well-defined. It's always well-defined. And because we're doing spectral decomposition, this implies that UIs are normalized and mutually orthogonal. All right, then there's purification of rho is constructed by doing this. Okay, so it's doable, right? That's the whole point. All right, so now let's go to more general, the transformation of transformation, right? How to find quantum circuit. Wait, I didn't. Oh yeah, so sorry. Okay, that was a purification. Now let's okay. So the original motivation was given this. Once you found this positive semi-definite matrix, how to find a quantum circuit that gives you this CPT lemma. So that was the motivation, right? So we went through purification. So where does this purification come from? So you're given some C12, right? You found this, and then you make a purification of this guy. And the purification, as you can see, requires as many dimensions as, at least as many dimensions as the principal system, right? So this dimension, the dimension of these extra systems should be equal to the dimension of the original subsystems, okay? But it's, we're assuming that we're only interested in the possibility and impossibility. We assume that it's always possible, right? So we purify this, and then next step is to bring this. This is 1, 2. And you apply unitary on this, yeah. No, it's fine. No. So let's try with this. So this gives some state. Let's call it eta on 1, 2, R1, R3, R1, R2. And then what we can see is that if you take a partial trace of on 2, 1, or 3. Then this is equal to identity on the first one. It should be R2. Right. Right. Now, so, and then if you also do take the parser trace of on the purified form of C12, right? Well, if you just take only the first two parser traces, then by definition of the purification of C12, you should get back to C12. And because C12 is found to be satisfy, where is it? This condition, right? And it should equal I1. So what we can see is that so this state, well, I shouldn't say state because it's not necessarily normalized, but this vector and this vector have the same reduced density state, the reduced density operator, when you just trace 2, R1, and R2. Now, there is a theorem that if you have a state, if two vectors have the same operator, when you take the partial trace, there always exists a unitary operator that's applied on what's traced out, and then which takes those two states interchangeably. So because of this equality here, this implies that there exists some unitary R1, R2, such that the pure C12 is equal to 2R1, R2, and eta. Right? So that's how you find 2. So that's how you find a unitary, right? That to implement your CPTD map that corresponds to this C. All right, that's more like an exercise to prepare yourself for a more higher order, so the next level of abstraction. All right. Yes. It does. That's right. But what's important here, it acts only on the bottom 3 subsystems. It's important it also acts on 2 because the reduced density operators, the reduced operators are equal after taking all these 3, right? So that's what's Any questions so far? Okay. Yes, please. Okay, that's a that's a very good question, which is something that I didn't actually explicitly say. So I said this is the maximum entangled state, but I lied a little bit. In fact, when you want to use these positive semi-indefinite operators to find quantum circuit, you should not. It's much better to use unnormalized state for this input state here. Namely that, so it's almost as a maximum entangled state. For example, for d-dimensional systems, d by d-dimensional systems, it should look like this. Like this, but so because you need this to normalize. But in this case, it's much better to use this bipartite density, bipartite operators, bipartite vectors that look like this without the density, without this normalization. Okay. Yeah. So this is something that you should be careful when reading papers. because they are both I've seen before. Now I think nowadays most people converge to this convention, but then again, people can do whatever they want, and sometimes, to be honest, I've also used this convention in my paper because we want to use this formulation to study programmability of quantum computers, and then if you imagine yourself providing that program as a quantum state, then it's much better to use this formulation because this is already a state, whereas this is not. Okay, so there's some subtleties in the formulation, and which can confuse even for experts. Well, I mean, I'm considering myself expert. I hope that's okay. So which can be also confusing for experts, but well, it's just something you have to check. Okay, but thanks for noticing. Yeah, that's a good question. Anything else? So far so good. Yeah. All right. So now, back to our original motivation of finding a quantum circuit that changes a quantum unitary, right? So the kind of circuit that we want to find is this. Well, maybe not this. All right, so we want something of this form that gives you, ideally, of something in this form. So f is some function that you want to implement. So in the first example, it will be making u into a control form. Okay, but this can be anything else you want. But suppose so this is something you specify a priori. All right. So and then the question is, given f, can we find rest of the circuit that achieves your desired transformation? Okay. Now the first step is to find is to learn how to define the Choi operator for for this kind of circuit. All right, let's do this. Right, so you take a circuit like this, okay, and let's label the density, the Hilbert spaces like this. Now, when you're studying quantum circuit, usually the input and output Hilbert spaces have the same label, but you can also imagine that these unitary circuits to be kind of like a channels. And then when you're studying channel, it's much more common to give different names for the input and output Hilbert spaces. Okay. Now that's just more of a matter of convention and so forth, but trust me that it becomes much mathematically clearer if we give different labels to input output spaces. Okay. All right. All right. So now this is okay. This is our starting point, and we want to find Choi operator that corresponds to this kind of circuit. So what we do is actually we add this. Okay. And then we just label this top one as the Hilbert space 1, and then relabel this as a copy of 1 with the bar, 1 bar. Oh, no, sorry. This is 2. Sorry about that. And then so 3 is this 3 becomes copy of 3, so we make a 3 bar, and then instead assign 3 to the other end of the maximum entangled state. All right, so that's how we make the Choi operator. Clear so far? All right, so let's define the C1, 2, 3, 4. Okay, so if we have this kind of circuit, we can show that this thing satisfies the following properties. So if we take the partial trace in 4 on C1, 2, 3, 4, this is equal to some operator on C12 on 1, 2, and then you get the identity on 3. So the reason you get the identity on 3 because if you trace out this 4, and basically it's almost the same as not applying this unitary. Hence also, and this tracing on 4 has effect on the partial tracing out on this 3 bar. And that's why you get the identity over here on 3. Now this C12 prime is actually basically this part. So it's almost like a CPTV map. In fact, it is a CPTV map because if we take partial trace on 2, you get identity on 1. Okay. And of course, the C1234 is a positive semi-definite operator. Okay. So now we can derive these equations, assuming that we have this kind of a circuit and beforehand. We can also ask the question the reverse way, right? If you can find a set of operators, so these C1234 and C prime 1, 2. If you can find a set of these operators, can you find a quantum circuit that corresponds to those operators? So in the end, the short answer is yes, of course, otherwise I would be telling you this, but you can do this kind of a reverse engineering technique that I've shown you here for the CPTP map, but basically define the purified state properly. Okay. So, so this is now almost in SDP compatible form of conditions. The reason I said almost is because if you remember the original formulation, basically you only have one semi-definite operators, right? But in the most recent one that I've shown you here is we have two positive semi-definite operators, two of these. So how do you make this compatible? Well, actually, what you do is you basically define one big operator and call basically the first section as C1234, and the other part is C12. And the rest can be whatever actually. Of course, well, not exactly whatever, because you have to make sure that C is positive semi-definite. So if C is positive semi-definite, then these submatrices are automatically positive definite. Yeah, so this is what you get. And then, so what about the linearity, right? So let's focus here. So this is not exactly yet in the, so let's focus here. So this is not exactly in the SDP compatible form because we want something like this, right? So basically we want something like this, right? So it's not like in this form yet, but the trick to do is this way. Like this. And so then you can see that it's linear in the C. Well, not exactly, because you have to put this in block form, but that's almost trivial. And then is equal to some constant, right? So now one of the conditions has been converted into the SDP compatible form. And of course, the other one is also very simple, namely that you start from this. And then basically, what did I do? Oh, never mind. I'm not copying the right section. Okay. So you trace out 2 on the C1 prime 2 minus the y2. This should equal 0. Right. Yes, please. So the question is, does this problem have a strong duality? And that's a very advanced question. And the answer is no. No, that's something to check. But usually, unless you define, unless you do something really funky, you should not worry about it. You don't need to worry about it. At least we did encounter some examples in the past when we do our research, not this problem, but in our research that we had to worry about this strong duality. But usually that's not, strong duality is not your main concern, trust me. Yeah, but if you've made that far, then you're pretty advanced in the state of the research. All right. Okay, so now just so this is just which we just found. So basically, STP compatible constraints to decide whether this thing corresponds to some circuit. Okay. Now, by the way, so just some terminology. So this form of circuit has been called a quantum comb in the literature. Because it looks like comb, when you want to comb your hair. But of course, in the past, it has been studied in different contexts, like for the quantum game, quantum strategy, in the context of quantum game, or quantum memory with a quantum channel with memory. So that's the quantum comb is, I believe, probably nowadays the most common terminology that's used to describe this. But it has been called quantum strategy in the context of quantum game theory, or quantum channel with memory, studying this as I would say kind of a channel capacity. Okay. Okay. All right. So now what we want is, so we learn how to describe this kind of quantum comb using an STP compatible form. Now the question is, we want to do this, right? We want to find it so that not only it is a quantum comb, but also gives you the desired transformation. All right, so it's almost there. Okay. Let's see. So the most important part is to how to describe this circuit using only the positive semi-definite operators C1, 2, 3, 4. Well, okay, let's do this, right? So again, we start by drawing this circuit diagram. Okay, so you bring your choice operator for the quantum comb, and then you apply unitary on this part. Okay, and then you do basically this, which is you do Bell measurement on these two subsystems. So what this does is you're basically doing quantum teleportation. So this thing, so this state, after it goes to the unitary, is teleported to this port. Okay. So you can see that at least mathematically, the bottom one is equal to top one. Okay, now let's try to describe the bottom one using the Choi operator. So let's give names to these Hilbert spaces. So that's 1, 2, 3, and 4 as before. And I'm going to divide this into 3 steps. All right. So the first step, you basically get your Choi operator. Okay. The second step, you apply this U to your second subsystem. So you get this. All right. Now the third step is to do measurement, this phi plus measurement on the second and third Hilbert space. All right, but we should in fact post-select on this state, right? On this outcome. So we're going to divide this by the post-selection probability, which in this case, because let's see if this were both d-dimensional system, the success probability of getting this particular outcome is 1 over d. So this is in fact equals 1 over d. Okay. So what do we get? So in the end, we get right. So and then what we next do is in fact, because there is so we combine this part, right? So because we want to make this look as close as possible to the standard STP form. So we just we combine this part to here, and we bring this U to dagger all the way here by using the cyclicity of the trace of the trace function. So this is in fact equal to hence. So d times, well, again, in fact, incorporate d inside. Right, so this is basically the Choi operator corresponding to this transformation. Okay, and what is nice about this is that again, this is it's already in STP compatible form. So the rest is just basically to make this, so we want this to equal some function of f of u, and then to the Choi operator corresponding to this is very simple. You just do this. Right? So if you set this to equal Choi operate this, then you already have an STP constraint, an STP compatible constraint to achieve this transformation for that particular unitary. Yeah, so there you go. So now you know how to find the desired function, or desired quantum cone with that implements your desired function. Okay. Okay. And I think it's a good time to stop here. I have more stuff to tell, but I think it's already late in a Friday afternoon. So if anybody has a question, I'll take no. Please. Oh yeah. So technically, so this equality for a top and bottom case happens only again. So quantum teleportation, you need to do Bell measurement here, but this outcome happens only 1 over d probability. Yes, that's the reason. Yes. Yeah. Yep. So, any questions?
So this mathematics actually kind of helps the composition of quantum circuit.
So this formulation helps to use SDP solvers to find whether there exists one quantum circuit or not. So only caring about the possibility or impossibility.
So this is a unique circuit, or there are other circuits that can have the same strength?
This, in most of the cases that we've encountered, the circuit is not unique. And so that's what you raised is a very important question, because, okay, so we use SDP solver and find out there is at least one unitary circuit, but what if we want more properties about the circuit, like depth, for example, like the extra quantum memory that we need to achieve this transformation. So these conditions, unless you can find SDP compatible formulation, we cannot incorporate that.
Mathematically, we can do like this for what we linear programming SDP. Well, I understand linear programming, but this something we have to program it with constraint and stuff for a quantum circuit.
So I think what you're asking is that, yes, so the standard SDP solvers are not directly compatible with this particular formulation, which is true, because first of all, standard SDP solvers cannot take any complex matrices, okay? But there is an interpreter that actually converts this formulation using Hermitian matrices into SDP solver compatible form. Yes. And I have actually extra calculation in my notes, which I can show you how to convert this. And then I can show you now later if you want me to do that. But rest be assured that if you can at least get to this far, somebody already have implemented the necessary functions to convert that to the standard form, which normal SDP solver can accept.
Add constraints. Like we have certain universal quantum gates. We cannot go, let's say, beyond that universal set of quantum gates. If we want to add those constraints,
or can we specify the universal set to make the decomposition? No, I don't know of any. At least not within this SDP formulation. It will give you like. It only gives you one. So even for the case the case of finding CPTP map, right? So the best you can find is that there exists some unitary that satisfy this equation, but nothing else. Yeah. Yes. No, phi is the phi is a constant, right? U1 is also constant in this case, right? So you want to find for C1, 2, 3, 4 that satisfy this equality in addition to these constraints. Yeah. Well, okay, SDP constraints should be both all of this combined with this part. Equality, yes. Yeah. Okay, that's a good question. So in this case, I didn't mention that, but because we were only interested in finding whether it exists a circuit node. So it's, for example, it was just max over 0, basically constant function. Yes, this is called sometimes SDP feasibility problem. It's also well-defined, well-studied field. But again, remember I mentioned about the probabilistic implementation or approximate implementation. In that case, you put as a maximization function to maximize for the fidelity, or maximize over the probability of success. And you can formulate that by exploiting that maximization function, which I completely ignore in this case.
criteria you fit into the estimate.
Yeah. Yes, exactly. Yes.
So this might be a kind of the same question. Actually, I kind of got to the last stage here. But so the first class, I think we were doing something with control injury.
Yes.
And like how to actually implement the quantum code. So can you kind of go back and kind of relate these stuff?
So short answer is that there is no direct connection so far. Okay, because I thought about how to. So the question was, I talked about control unity at the beginning. Then I went to talk about STP formulation of this finding quantum comb. But what's the relationship, right? To be honest, we so far at this point don't know of any direct reformulation of this control unitary problem in STP. Because one of the reasons, what is the reason? Actually, I don't know why. I think we just kind of, there are so many other problems to solve beforehand. And I guess we just haven't got that far. Right, so right now we don't know, actually, yeah. But this is like the original motivation to study this kind of higher order transformation. So yes. It's one one comb, yeah. Oh yeah, we can have this multiple calls by doing this and up and down many times. Yes, general comb, yes. But the problem is that for each slot that you add, the semi-definite operator you want to solve grows exponentially in the size. So good luck. Yeah. I mean, there are some techniques to exploit to reduce the size of the problem, but still it's exponentially scaling at its heart. So sorry. Yeah. So, all right. Congratulations. You guys have made this far, and thank you for your attention.